Hello, welcome dear participants to the INSPYRE 2021. Today we have a very special day because we are going to bring you visiting our laboratory, actually the Laboratori Nazionali di Frascati. So we are going to show you our infrastructure, starting with the accelerators. We have here one of the very few colliders in the world working even now. Now, of course, it stopped because otherwise I couldn't go inside. So I'm going to show you the DAFNE electron-positron collider together with the experiment we are running in this period, which is named Siddhartha. Also, I want to tell you that this infrastructure is part of the European project Strong 2020, which is financing access of users coming from abroad to this infrastructure. This visit inside the collider will be followed by a very nice visit in our visitor center, where you will learn some very interesting news and some very interesting skills of how physics is being done in these days. So we start, follow me, I'm going to put my protection. So follow me, we are just going into the restricted area of the DAFNE electron-positron collider. Come with me. Here we are. So have a look how beautiful it is, this machine. How many colors, how many elements. So this is a machine which has been built in early 90s to do research in the field of particle and nuclear physics, with an aim to study processes which go from the disappearance of the antimatter in the early universe to search for possible departures from the standard model, and in this context also dark matter, but also it's run right now to study the processes of interactions of the so-called strange quarks with the normal matter, which might be very relevant for the neutron stars. So we used accelerators also for studying the stars, which is something to me very much important and very dear. Also, this machine, let me show you something. So come with me, I want to show you something. So have a look here. This machine, it's also having a very strong and intense beam of synchrotron radiation. You might see here that these are lines which actually bring the radiation which is produced inside the accelerator in some experimental holes which are beyond this wall. And what we study there are processes which are relevant for biology, for example, for tumors, or also for material science, new types of materials, new type of electronics. So it's not only research in particle field and nuclear field, but also experimental research, which is ending up in biology, in medicine, and in industry. However, so let me tell you something about the way in which this machine is functioning. So please have a look here. You see many colors. So practically all these colors are elements of the machine. There are actually here two rings, so it's a bit difficult to see them, but look at the colors. There is the green, then there is the orange, which belong to two different rings. In one of these rings are circulating beams of electrons, while in the other one, the beams of anti-electrons, which are also called positrons. And all these colors belong to different type of magnetic elements. So there are dipoles, quadrupoles, sextupoles for more than 200 magnetic elements. Then there are, you see there are the white cylinders. You see that? that white cylinders are a very important part of the machine because they are vacuum pumps. So you need to do the vacuum inside such a machine in order to allow to the beams to circulate and not to collide with the residual gas inside. So you also need to be a very, very skilled vacuum engineer to run such a machine, because the vacuum here is more or less like the one on the moon or even better. Then have a look in this direction. You see that big pink, pink apparatus. That's an experiment which was run something like a bit more than 10 years ago. It's called FINUDA, and was studying processes with strange quarks inside the nuclei. And what is this machine doing? Actually, it's colliding electrons and positrons, boom! So when electrons meet the positrons, they annihilate, and they create, at the energies of our machine, they create the so-called strange quarks in the form of so-called kaons. The kaons are a peculiar type of matter. They are called mesons, and they contain inside the strange quark, which we are studying inside our experiments. And that's a very special machine, because it's the machine which produces the kaons with the smallest energy in the world. One might be shocked why you are interested in small energy particles when everybody runs for high energy. But actually, in our case, we want to have small energy kaons, and I'll explain you in a moment why, because that's what we do in our experiment, which is called Siddhartha. So follow me. I want to show you something about our beautiful jewel Siddhartha experiment, which is studying physics right here, but to understand the stars. Follow me. Okay, here we are. So we are just facing now the Siddhartha apparatus. Look at it. So it's just behind me. That's an apparatus which is studying the stars, the strangeness processes which are relevant also for the stars. So you might see there this apparatus which is above the so-called beam pipe, namely where these electrons and positrons are colliding and producing these charged kaons which contain the strange quark. And what it is being done in that apparatus is that the negatively charged kaon, it's stopped inside the target, and there it forms kaonic atoms, which means an atom where the electron is replaced by the kaon. And since the kaon is much fatter than the electrons, actually it's 1,000 times heavier, this means that the orbits of this exotic atom are different. So what we are studying is the decays, the excitation of this atom, which produces X-rays. We measure those X-rays so to extract the energies of this level. And we measure so with some detectors you cannot see because they are closed inside the white cylinder under vacuum at minus 120 degrees. So to work optimally, they are silicon detectors, silicon drift detectors, which measure these X-rays. And when we measure them, the process is very rare, so it's very difficult to do so. Actually, we are now aiming to measure for the first time in the world the kaonic deuterium, which has never, it's too difficult. So we hope to succeed, of course. So once we succeed to measure those exotic atoms, we can extract the contribution of the strong interaction on the levels of the kaonic atom, so deduce how heavy, how strong is the interaction of strange quarks with the others. Do they embrace strongly or they are very mild? And on this depends also the role of the strangeness inside the heart of the neutron stars. And if you want to know more, just ask me in the session of after the video, of course. Ask me questions about detectors, about the stars, about what exactly and who we are, Siddhartha, to do this type of studies. Okay, so where are the electrons and positrons coming from? Of course, you don't buy positrons in the supermarket, so you need to produce them elsewhere and inject them inside the DAFNE collider. Well, actually, DAFNE, it's a complex of accelerators. I only show you the final end, namely the rings where you have the collision of the electrons and positrons. But you produce them elsewhere, just in a linear accelerator, where you produce positrons out of the interaction of electrons inside the target, where also positrons are produced, extracted, accelerated. And you see here, these are the two lines, this one and the other one, where the electrons and the positrons are being injected from the ring, which is the accumulator, inside the DAFNE collider. And you see again behind me part of the machine with the beautiful colors which belong, as I told you, these are vacuum pumps, the white cylinders, while the other ones are quadrupoles, for example, the yellow ones, and other magnets which are keeping the beam squeezed and circulating inside the rings, so that we can use them and collide them to produce strangeness and study this strangeness in our experiments. Now let's go, proceed, and let's go to see closer how Siddhartha is being done. So once again, we go to see the running experiment. Even in this difficult period, we are still running an experiment, and let's go and have a look. So let's proceed. So here it is, that's the Siddhartha experiment. So you see here that it looks, actually it is a very complex machine. So in order to be able to measure small signals, which are our X-rays produced in the decays of the kaonic atoms, you need to have special attention, because these X-rays are not produced uniquely by your exotic atoms. There are all series of other processes which have nothing to do with what you are interested in, and you have to practically dump and avoid that as much as possible. So one of the things you are doing is to protect your apparatus with screening it with lead shielding. But that's not the only thing you are doing. Well, actually the real detectors are inside that white cylinders. As I told you, they are silicon detectors. But a part of that detectors, you have a series of other ones which tells to the silicon detectors that when they are reading a signal, this signal, if this is the case, does not come from kaonic atoms, but come from something different. And let me show you closer how this is happening. Come with me. Okay, so let's have a closer look to our apparatus. So this is Siddhartha, and as I told you, there are some helpers. So we need help to read the signal and to disentangle it from X-rays which are background. One of the helpers, which is called a veto system, because it's vetoing what it is not signal, are, you see, these black detectors outside, which are scintillators read by photomultipliers. So whenever the scintillator is reading a signal in coincidence with our silicon detector, this signal comes from outside. So it's clear it cannot be produced inside the apparatus where there is a target. The kaonic atoms are produced with kaons coming from the beam pipe from below. So when this happens, this means that what you are looking for is not your signal, so you can nicely throw it away and look only for those which are not vetoed. And there are many other tricks an experimental physicist need to use when doing an experiment. Among other things, look here. So look at this readout electronics. And that's a small experiment after all. Can you imagine this multiplied by 100 in the really big experiments? So this is a kind of short story about our collider, the DAFNE electron-positron collider in Frascati. And again, a short story about our Siddhartha experiment, which measures the strong interaction in systems with strangeness. And we will also have, I remind you, the visit to the visitor center. Stay with us and prepare your questions, because then we go live and we go to interact with you and to help you out and answer all your curiosities and questions which might have rise while looking at this video. Stay with us.